A U.S. Navy radar operator stared at his display in growing alarm. Just hours earlier, satellite intelligence had confirmed a routine patrol. A single Chinese Type 52D destroyer operating alone in international waters, 200 miles southeast of Taiwan. Now, his screen tells a different story entirely. 7 distinct contacts spread across 30 miles of ocean, each displaying the unmistakable radar signature of a major warship. The formation moves with military precision. Destroyers, frigates, and what appears to be a cruiser taking point. The radar operator frantically checks his equipment, certain there must be something wrong with it. But the contacts remain. One Chinese warship had suddenly become 7. Electronic warfare has its roots in the early 20th century, when militaries first realized that controlling the electromagnetic spectrum could decide battles. During World War I, crude but effective methods emerged, intercepting enemy radio traffic, decoding it, and in some cases, blasting out powerful signals to drown out enemy transmissions. The aim was simple: deny the opponent the ability to coordinate their forces while safeguarding your own communications. Even at this stage, a well-timed transmission could turn an expensive communications network into dead air. By World War II, these early ideas had grown into sophisticated operations. Radar, a technology barely a decade old, became a critical target. Both Allied and Axis forces experimented with radar deception, flooding enemy scopes with false echoes, blinding them with metallic chaff clouds, or luring them into reacting to phantom fleets. Operations like Britain's Window and Moonshine proved that an enemy's most advanced sensors could be rendered useless by the right electromagnetic trick. In the Cold War decades that followed, navies became even more reliant on radar, long-range communications, and eventually satellite links and precision-guided weapons. Electronic warfare kept pace. The United States and its allies developed systems capable of jamming multiple frequencies at once, detecting and deceiving radar from hundreds of miles away, and coordinating sensor data from multiple platforms into a single resilient picture of the battle space, a capability that made simple single-source jamming far less effective. As China positions itself as the United States' main rival in the Pacific, it's begun exploring whether innovative approaches to electronic warfare could potentially undermine American dominance of the waves and give itself the upper hand. The roots of China's electronic warfare program stretch back to May 1965, when the Beijing Institute of Tracking and Telecommunications Technology, or BIT, was established as part of Project 651, China's ambitious plan to launch Dongfanghong-1, the nation's first satellite. Initially tasked with designing radar facilities at the Xuquan launch site and coordinating China's emerging space control network, their engineers were learning skills that would prove more versatile than anyone imagined. When Dongfanghong-1 successfully reached orbit on April 24, 1970, BIT had proven its mastery of satellite tracking and communication systems. But the Institute's role quickly expanded beyond peaceful space exploration. As China's primary system design contractor for aerospace measurement and control, BIT began accumulating expertise in precisely the technologies that modern electronic warfare requires: advanced radar systems, signal processing, and the ability to manipulate electromagnetic signatures across vast distances. By the 2020s, the Institute had grown into a major military research complex with over 500 scientific personnel. It had international cooperation projects with over 20 countries, providing additional insights into foreign radar technologies and vulnerabilities. While officially focused on civilian aerospace applications, this knowledge base was creating opportunities that China's military planners were undoubtedly beginning to recognize. Researchers weren't just tracking satellites anymore. They were developing a sophisticated understanding of radar signatures and electronic countermeasures. Few outside observers had paid attention to BIT's growing capabilities during the past 4 decades. After all, satellite tracking seemed like a purely defensive technology. But the same expertise required to monitor objects in space could theoretically be reversed. In May 2025, researchers at BIT published a peer-reviewed paper in the Journal of Systems Engineering and Electronics that sent shockwaves through naval intelligence communities worldwide. The team, led by researcher Hu Zhijun, claimed to have solved one of electronic warfare's most challenging problems: how to make a single warship appear as an entire fleet on enemy radar screens. Their approach was unconventional. Instead of relying on complex and expensive radar decoys, they use remarkably simple hardware, a 1-bit signal processor that records only whether an incoming radar wave crosses a set voltage threshold, paired with advanced coordination algorithms. 4 synchronized electronic jammers equipped with those minimalist chips could, in theory, sculpt the electromagnetic environment in a way that fooled radar systems into mapping multiple vessels across a wide stretch of ocean. The processor's speed allowed each jammer to adapt instantly to changing conditions, preserving the illusion as the phantom ships quote-unquote moved. According to the paper, computer simulation showed the effect could be devastating. Radar-guided anti-ship missiles consistently locked onto the fake targets, leaving the real vessel invisible and free to maneuver. In these tests, enemy systems wasted expensive munitions on empty ocean, while the genuine threat slipped away. Yet the researchers acknowledged serious limitations. Their findings came entirely from digital simulations. No live trials against real missiles had been conducted, and the system's stripped-down design could be defeated by modern network missile systems that cross-reference radar data from multiple sources. Advanced navies like the United States already use frequency hopping, signal correlation, and other countermeasures tailored to defeat basic jammers, making the method's battlefield effectiveness uncertain. Even so, the timing and openness of the announcement puzzled analysts. Why reveal detailed specifications for what should be a closely guarded capability? Some saw it as a calculated act of psychological warfare, meant to plant doubt that billion-dollar missile systems could be undone by inexpensive jammers. Others suspected deliberate misdirection, feeding foreign intelligence agencies an idea that might waste their time and resources. Whether genuine breakthrough or carefully staged theater, the Ghost Fleet concept forces adversaries to second-guess what they see on radar. But the Chinese researchers aren't stopping with computer simulations. According to BIT's published plans, as well as integrating artificial intelligence into the 1-bit processor system to improve its resilience against countermeasures, the next phase will move toward live field testing, a transition that will reveal whether their Ghost Fleet concept can survive contact with real-world electronic warfare environments. This progression from laboratory to operational deployment follows a familiar pattern in Chinese military development. Beijing has consistently demonstrated a willingness to announce capabilities before they're fully proven, using technological theater as a form of strategic messaging. The Ghost Fleet announcement may be designed as much to influence American naval planning as to showcase genuine capability. For U.S. Navy strategists, the mere possibility of such technology creates a planning nightmare. Even if the Chinese system proves only partially effective, American commanders would be forced to treat every radar contact as potentially deceptive. This uncertainty could paralyze decision-making in critical moments, particularly during the opening phases of a naval conflict, where rapid target identification determines tactical advantage. The implications extend beyond immediate military applications. If China can convincingly demonstrate Ghost Fleet technology, it may trigger a broader electromagnetic arms race across the Pacific. Allied navies would need to develop countermeasures, while potential adversaries would rush to acquire similar deception capabilities. The result could be a new category of warfare, where electronic illusion becomes as important as firepower. American defense contractors are likely already exploring responses. Advanced radar systems with AI-assisted target discrimination could potentially see through coordinated jamming by analyzing subtle patterns in radar returns. Multi-platform sensor networks might cross-reference data to identify phantom contacts. But each countermeasure would require significant investment and development time, giving China a valuable head start. While the technology's limitations remain substantial, the Ghost Fleet concept highlights the growing importance of electronic warfare in naval operations. As missiles become faster and more precise, the ability to confuse targeting systems becomes increasingly valuable. The Phantom Fleet now looms on the horizon of naval warfare. The question facing Pentagon planners isn't just whether the technology works as advertised, but how to respond to an adversary that may have turned radar screens into funhouse mirrors.